Hi everybody, welcome to this week's belated recording in lieu of an actual lecture. Now, hopefully everybody has seen the announcement regarding this. If you haven't, please go ahead and take a look at the announcement that was posted on this topic, but fortunately I was a bit unwell yesterday. I wasn't able to do the lecture live, so this is a follow-up recording. It's going to be formatted a little bit differently because we can't do the live side of things well. Also, as I also noted in the announcement yesterday, big thank you for those of you who flagged some missing content. Now, because there was missing content, it means that we can't really cover as much as I would normally expect to in this week's session. That's not a huge deal, but it does mean that we're going to have a bit more to cover next time around, which we'll get to in just a second. Okay, so what is happening in event-driven computing this week? Well, first of all, I'm busy marking your programming assignment 1s. That's important because the withdraw no fail date is coming up. That is coming up on the end of this week, last day to withdraw no fail from the course. So obviously we want to have some results in before then. So that's what I'm busy working towards then. Now, on that note, I can't mark your work properly if I don't have access to your GitHub repository. I'm aware that wasn't in the original assignment specification. That's why I posted about it in an announcement last week. So please go ahead and share access with my GitHub user if you haven't already done so. And I'll be contacting people over the next few days if I still can't get access to your work, but I can't mark your work and give feedback if I don't have access to see your code base, to see your commits and your comments. So basically, marks will be coming in this week or after I get access to your repository, whichever happens later. So if I don't get access to your repository until next week, I'm not going to be able to give you marks until next week. Assignment 2, that's available, as we discussed last week. It's due at the end of week 9, so you do have the 2 weeks of mid-semester break to work through it, but this is by no means a straightforward assignment, as similar to what many of you discovered with assignment 1, how there were components to it that really required a bit of planning and working through to get going before you actually brought everything together with the code. You can't just code this on the fly, and I expect you to be building based off of a Petri net. Planning the Petri net is a really big part of this assignment, so please make sure that you get started on that, start planning out your Petri net. The interface file for getting started with your coding is now available, but hopefully you've all been looking at your Petri nets for the time being before actually getting stuck into the code, but that is available now. There aren't workshops this week because it is an even week, but because this recording isn't live, there'll be an extra Q&A session on Zoom on Thursday. That would happen in the usual time that we would have our workshops if it was a workshop week. So that's what's going to be happening there. Now, things are going to get a little bit weird as well after the mid-semester break, because Monday after the mid-semester break in week 9 is a public holiday. So we might have to do something a bit similar then. That week, however, is a workshop week. So we'll figure something out. Start to have a think about what you want covered in the recording, and I'll be putting out a survey over the course of the next week, so that once you've had a look at the notes in the book and maybe you have some questions at that point, have a think about what you want me to actually work on or go through in that lecture time, and that's what we'll be doing. So there'll be a survey about that. Okay, so this week we introduced the concept of functional reactive programming, and we've moving on from the observer model. So previously last week we looked at the observer pattern as a practical way of dealing with dynamic event-driven code. How do we deal with events when we don't necessarily know what's going to happen when an event is triggered? What happens when we are developing events to some sort of API? How do we deal with that? One way we dealt with that was with the observer pattern, but the observer pattern itself has some drawbacks in the way that it handles things. So and those drawbacks are related to the fact that the observer pattern effectively tries to shoehorn event handling into standard object-oriented procedural programming, and that just causes all sorts of problems. It would be great if we could program in a way that was designed for handling with events in the first place. That's what functional reactive programming is about. So what is functional reactive programming? What is its role? Well, it contains two components, the functional nature and the reactive nature. The functional nature, we've already seen a little bit of that as we are programming out our systems. You would have seen in the example code that the event sources trigger a function of some sort. So we are really programming to the fact that our events are going to be triggering functions, and we write our code using functions to define what happens in every case rather than trying to rigidly structure everything in terms of objects. We define behavior in terms of functions, and we can do that somewhat dynamically. That's what functional programming is about. One of the ways that I like to think about functional programming is in terms of mathematical functions, but also just other types of functions that you use in every day. So if we think about a mathematical function, maybe we have something like f of x equals x plus 2. So y equals x plus 2, and for every x that we put into the function, we get out the result x plus 2. And as we change the value of x, the value of the result changes as well. One of the things about functional programming is this idea of continuous versus discrete. In a perfect world, we would be able to properly have continuous functional, and by that I mean a good example for this is a light switch, or sorry, not a light switch, a dimmer knob. So for example, if I have a knob and its initial value is 1, as I turn this knob here, its value is going to be going up, and then the result of the function goes up in turn. It's continuous. There are no separate discrete values. However, much like a dimmer switch, for those of you who are familiar with the electronics of how a light dimmer switch actually works, as you change a dimmer switch, it doesn't actually change the brightness of the light itself. What it does is it changes how often it switches the light on and off. It's not the value that is changing continuously, it's a series of discrete events that are happening at different intervals, and that's what rotating the dimmer switch actually does in a real system. And it's much the same with functional programming. We think about it in terms of, well, okay, x is this magical value that always represents, y, the result of this function, f of x, represents the value of x plus 2 at any given time. And at any point in time, if we change the value of x, then the function will always result in x plus 2. And no matter how frequently or how often we change the value of x, immediately we get this x plus 2 value out. Now, we can't actually achieve that in our programming because events are discrete. They happen when they happen, but they are not this continuous source of change. But what if we treated them as if they were? Because a lot of times events that occur in system do represent continuous sources of change. The events represent me, turning the light dimmer, and as I turn it, I get new discrete values for each position that I come across with the dimmer switch, and I'll get a series of discrete values, and I want some sort of update to occur based on those. So it's all a bit abstract, but that's kind of what we're going for. We're going for this continuous change in reaction to values and events in our system. So that said, let's take a look at how we might actually achieve this in code. Now, we've already looked at how this might be done with listeners, or we've seen the basic idea of listeners, where we have we set up a class, we register our listeners onto the class, and then whenever some event occurs, that results in the listeners being called. Now, functional reactive programming framework provides effectively an optimized way of doing this, and more. And that's what the Sodium framework and many of the others that you might be familiar with, if you're familiar with them, do. So let's go ahead and take a look at an example. Okay. Now, using the Sodium framework, now, as some of you may have used, some of you may be familiar with the RX framework, which we were looking at a bit last year, but we're using a slightly different framework this year called Sodium FRP. Some of you may also be familiar with other reactive frameworks, not necessarily functional reactive frameworks, but reactive frameworks from the web side of things. You might have some familiarity with frameworks like Angular, Vue, React. These are reactive frameworks that are all designed to allow us to program in such a way that the state of the system always reflects the data within the system. And it does that automatically, reactively, and that's somewhat what we're going for here, with some added layers on top, and we'll get to those layers. So this piece of code, what are we looking at here? Well, we have a basic class with a main method, and I have these two cells, and cells are our reactive variables. So when one of these changes, well, it's a cell sync because it allows me to put values into it, but a cell is a reactive variable. When it changes, things update because of it. And let's say that I wanted to define some functions that are going to automatically update, or I want to define some variables that automatically update as a result of changes to these input variables. How would we do that in functional reactive programming? Hopefully you've already seen some examples of this. I thought I'd start with a slightly more discrete example rather than the GUI examples that you're seeing in the text. So let's go ahead and create a few new reactive variables. So I'm going to create 3 cells. I'm going to make them all integers as well. And I'm going to call the first one sum. And I want sum to represent the sum of number 1 and number 2. This is like the basic stuff that that you might be familiar with in your introductory programming courses, just from a different approach. So we want to set this up so that sum always reflects the sum of number 1 and number 2, and then whenever we change number 1 and number 2, sum is going to automatically update to reflect that. And we do that with our functional reactive approach. And the way that we do this is we are going to use the lift function. So I'm going to invoke the lift function on one of these variables, and I'm going to add the other variable in there. So the lift function just allows us to do something, perform some action when one of these reactive variables changes. We have to call it on a reactive variable to start with. However, we can invoke as many different variables as we like as a result of this. So now we're using something called a lambda function here to define the behavior that occurs when the lift gets called. So whenever number 1 changes or number 2 changes, this lambda function gets triggered. This is where the functional part comes from. You might be familiar with anonymous functions from other programming languages or lambda functions in other programming languages. This is just another invocation of that. Okay, and then whatever I return here becomes the value that sum gets whenever number 1 or number 2 changes. So in this case, n1 and n2 represent the actual raw values of number 1 and number 2 at any given point in time. So I want to return n1 plus n2. And this means that anytime number 1 changes or number 2 changes, the sum is also going to get automatically updated, which is nice. Let's just take a look and see how that works. I'm just going to do .out.println. I'm going to add a print line, and we are going to invoke. So we're going to start by grabbing number 1. Now, cells are a special data type. We can't just retrieve their values by calling it directly. No, actually, we could try. Let's try and find out. That would be very convenient. But I think we're probably going to have to call sample on that to see. And sample is a method for retrieving the current value at any given point in time. But let's just see what happens if we print them. Sum. Okay, and what I have here is I have some code here that is going to, I'm just going to copy this down here. I have some code here that is going to take an input from the standard input, so I can type numbers in on the command line. It's going to, every time I put in a number in on the command line, it's going to update the value of number 1. Number 1, of course, is initialized as 0, but number 2 starts at 10, so it's going to update number 1 every time it updates number 1. That should update the sum. And yes, this basic code is very much like observer pattern listener code. It's just a more elegant way of writing it, but we will get into a little of the more complicated, fancy stuff in a moment. So let's just go ahead and compile this, and yep, and what have we got here? Yep, alright, so I'm going to have to actually call sample, because it's not just a regular integer that I'm dealing with here, it's a reactive variable. That's okay. Well, let's try that again. Almost there, what have I got? I think I've missed something somewhere. Probably missed a bracket somewhere. Just roll it back here. Okay, line 11, what have I missed? Yep, I have done the wrong type of arrow. That's better, okay. Save that. Wrong type of arrow, people. Okay, there we go. Okay, so number 1 is 0, number 2 is 10. Let's change number 1 to 5. And we can see that when number 1 updates, sum automatically updates for us. We can extend this through other functions as well. The nice thing is that all of these functions are treated separately. So let's have difference, for example. Which is a subtraction. and we can throw product in there as well, or multiplication. Here as well. And compile that and run it. Okay, so number 1 is 0, number 2 is 10. The sum, number 1 plus number 2, 0 plus 10 is 10. Difference, 0 minus 10 is minus 10. Product, 0 times 10 is 0. Okay, let's go with 10. Okay, 10 plus 10 is 20, 10 minus 10 is 0, 10 times 10 is 100. So every time I change this variable, in this case it's just changing number 1, but we could make it change number 2 as well, and number 2 would update accordingly. So we've set up with very little lines of code a system that is automatically reacting to changes, and we are declaring the way that these reactions are happening up front rather than having to explicitly write this listener registration-y kind of code to framework everything together. So it's somewhat taking this approach for us, but things are a little bit more powerful, which we'll talk about right now. So that was that example. One of the interesting things about functional reactive programming is we start to think about, okay, well, if we have this sort of stream of data coming in, this stream of events coming in, if we have these variables that are changing, what can we do with that? So before we were talking about this idea of a variable being like a dimmer light switch, and if we have a couple of different variables and we change those in different ways, as their values changes, the rest of the program change as well. What other operations might be useful for us when we have multiple sources of inputs into a system that whose values can affect different types of change within the system? The way that we tend to think about that is, well, the way that we've been thinking about that up until now is that each of these inputs are completely discrete and separate, right? So this input here, it receives a change, or some value comes in on this input and we go, okay, well, we need to react to that specific value changing. And then this one changes and we go, okay, we'll react to this one changing, and maybe there's a relationship between the two, but it's like, okay, this one changes, and then we have to go and check what all of the others are. And wouldn't it be nice if we could think of all of the inputs as a connected system? And that's one of the problems that functional reactive programming frameworks like Sodium, like RX, try to solve. So they say, okay, well, we have these multiple inputs, and we just saw an example of that where we have two inputs and we've combined them together to form this one output whose value, as we do this, maybe this one changes accordingly. That's nice. But so far we've only looked at basic arithmetic operations. What other operations could we potentially do here as we receive inputs from various different sources? If we treat inputs as a stream, as a flow of events through the system, how can we handle it? And we can start to do some interesting things, like we can say, okay, well, as we receive inputs from here, we maybe only propagate those inputs forward if they meet a certain threshold. We could filter out values from these inputs. We could combine multiple inputs together, as we just saw. We could interleave inputs from multiple different sources. We could group them together so that they all get treated the exact same way and handled by the same set of handling functions. And those are some of the benefits that we gain when we use functional reactive programming. When we start to, instead of treating each event, each occurrence within the system as a discrete and separate event, we draw relationships between the events within our systems. We treat them as flows of data, and we can then start filtering and manipulating that data to achieve the outputs that we want, rather than treating everything as separate, discrete occurrences within the system. And that is what we'll be looking at over the next few weeks. So we talked about how we can deal with two discrete variables changing, impacting another variable. But events themselves are not just variables. They are things that occur within a system, and they come in at various different discrete times. So one way that we can think about it is that we have this source of events that occurs over time. So if we have time down here, and we have events that occur every so often, we want to think about the system as this continuous flow of change, but realistically it's separate discrete events that we have to deal with. So we have each of these events, and we treat them as a sequence or as a stream, rather than as discrete individual events. And we can say, okay, well, maybe as we receive these events through the system, maybe this event has a value of -5 attached to it, whereas this one is 0, this one is 1, and this one is 3. Because events don't necessarily just represent a switch being pressed. It can represent like a value being input into the system. So the value changes from 1 to 3, for example, when we take a more high-level view of it. So for example, we might have these values here. Maybe we want to lose the negative values from the system. So we can represent that as all of these coming down here, and this one gets left behind. Something like that. This is called a marble diagram, and we'll see a few little incarnations of this floating around the reference material as you go through it. But it's a useful way of representing how events occur in the system. What can we do with events coming from multiple sources? So maybe I have an event source here, an event source here. Maybe these are two different knobs, or two different volume controls that can, be changed. And these represent the values of those each time that they are changed. But maybe these control similar things, so we actually want to group them together. Well, with this approach, we can say, okay, well, let's actually pull all of these inputs into a single stream of inputs. And then we have one stream to deal with, and we can apply all of the same transformations and outcomes to this stream. So maybe, for example, we needed to subtract 10 from each of these values for whatever reason. Maybe there's like a constant that we have to interact with, or we have to multiply everything. we can do that and we can apply that to the stream. Maybe we want to see how these values compare to each other over time. We can compare these values when we treat them as a stream of inputs rather than completely separate, discrete inputs into the system. So that's what we're aiming for, and that's what we're going to be looking at in more detail over the next couple of weeks. And then furthermore, we're going to be looking into stream brokering and stream handling and how this can actually get used in industry with streaming frameworks like Apache Kafka, which is used for handling and brokering multiple different sources of events coming from lots of different services in large-scale software systems. So that's all for the moment. Enjoy your mid-semester break. Don't forget to start early on your PetriNet assignments. And if you have any questions or you want to ask me about your progress in the course, you have any questions before the withdraw no fail date, please don't hesitate to ask me via my uni or email. I'll be around. For those of you who have questions about any of this content or any of the other functional reactive programming content that we're going to be looking at over the coming weeks, I will be available Thursday during our usual scheduled Zoom workshop time, which normally happens on odd weeks. So I'll be available this week during that time to answer any questions that you have about this or anything else related to the course. So we'll see some of you then. Otherwise, have a good mid-semester break.